Dear colleagues, dear audience, today we start the second day of our online workshop, the second lecture of Professor Kyung Lee from Chennai National University on the second lecture of Differential Dynamical Systems. Professor Lee.
Okay. Hello, everyone. In my second lecture, I will talk about differentiable dynamical systems. In the first lecture, I talked on motivation of dynamical systems and the classification of dynamical systems, and finally the goal of dynamical systems. The goal of dynamical systems is to understand the long-time behavior of dynamical systems or asymptotic behavior of the orbits of the dynamical systems. Okay, there are many ways to describe the long-time behavior of the orbits of the system. One of them is done by Steve Smale using the basic knowledge of differential topology in early 60s. We call the subject differentiable dynamical systems. Yes, Steve Smale is one of the pioneers of differential dynamical systems. He got the Fields Medal in 1966. For our differentiable dynamical system theory, we let M be a compact, smooth manifold with a finite dimension. And Tm is the tangent bundle of M, that is the union of Tp of M. A vector C1 vector field on the tangent compact smooth manifold is a C1 map from the manifold M to the tangent bundle. Tm is also a manifold such that at every point in here, x of t is the tangent vector belong to Tp of M. In this case, we say that X is a C1 vector field on M. And the C1 vector field X can be considered as an ordinary differential equation on the manifold, and it induces a C1 flow phi. I will denote it by phi. Sometimes I will denote it by X of t on the manifold. For convenience, I will denote capital X1 of M is the set of C1 vector fields on the manifold with the C1 topology. Our goal is to understand the dynamics on the manifold. So using the dynamics on tangent bundle, Smale characterized the dynamics on the manifold from topological or ergodic point of view. So to understand the dynamics on the manifold, long-time behavior or asymptotic behavior of the orbits given on the manifold, Smale used the dynamics on the tangent bundle. So among the tangent dynamics on the tangent bundle, like hypervelocity or quasi-hypervelocity, dominant spreading, or partially hypervelocity, or singular hypervelocity, or multi-singular hypervelocity, a lot of a concept on the dynamics on the tangent bundle. So, to understand the dynamics on the manifold, Steve Smale used the dynamics on the tangent bundle Tm. Among the tangent bundle dynamics, the notion of high probability is most useful and important to understand the dynamics on the manifold. So let us review the concept of high probability. We say that a compact invariant set. Invariant means if you take a point in lambda, then the orbit still stay in the lambda. So if you restrict on lambda, then the system is also again a dynamical system. So it is a subdynamical system. So compact invariant set is high probability for the vector field if there is a continuous splitting. Continuous splitting means for any point P in lambda, tangent space Tp of M can be decomposed stable space at P and the unstable space of P, and the XOP is a vector. So this is bracket indicate the one-dimensional space spanned by this vector XOP. At every point P in lambda, tangent space can be decomposed by three spaces, subspaces: stable space, unstable space, and the one-dimensional space spanned by X over P. It's continuous splitting. So stable space means derivative of the flow is contractive on the space. It means if you take a vector in here, the norm of the vectors is less than or equal to C times e to the minus t of norm of V for every positive t. It means time goes to infinite. The norm of the right side goes to 0. So exponentially. But because of the capital C, in a finite time doesn't matter. If time goes to 0, time goes to infinity, the norm of the vector goes to rapidly go to 0, exponentially goes to 0. And on the unstable space, derivative map is expansive on the unstable manifold. It means derivative is linear. So negative time it is contractive. That is, for any vector V in unstable space, dx minus of V, negative time, then it is contractive. So t goes to infinity, bigger and bigger. Then the norm goes to big, go to infinity. So we have three properties. First, continuous spreading. Derivative map is contracting on stable space and expansive on unstable space. We say that vector field is anosoph if the whole space is hyperbolic for the vector field X. If P here, we note that if P is a singularity, fixed point, the singularity, then this vector is 0. So dimension of the tangent space must be dimension of the space, stable space plus dimension of the unstable space. So in the high probability set, every singularity is in some sense isolated. Let me explain by figure. Let's take a point P. If it is not singularity, then we have the regular orbit like this. This is the orbit. So xt over P, t in R. Then we have the vector here, x over t, tangent vector. Then we can have the x over bracket x over P is the one-dimensional space. And NP denote the normal space. This space can be expressed by stable space, direction unstable space. In this way. So if you take a vector V in the stable space, then the norm, finite time doesn't matter. But ultimately, the norm of the vector goes to 0. This means the norm of the vector go to increasing and increasing, go to infinity. If time go to minus infinity. Also, if you take a vector in the unstable space here, the norm of the vector goes to 0 as time t goes to minus infinity. So it goes to infinity as time goes to infinity. So this is the stable space, because if you take a vector in ES, then the norm goes to 0 stably. And if you take a vector in here, the norm of the vector goes to infinity. So let me give you a very fundamental example which has the hyperbolic structure. That is Smale's horseshoe. To introduce the notion of Smale horseshoe, we start from this unity disk here. This is the unity disk here. And L map is linear. So L is what? Contracting around the x-axis and expanding around the y-axis. Here is the formula. For example, x point y send to 1 over x, comma 5 times y. So here, red colored part send to this part, green colored part go to this part. And then the map G implies the in the center part bend and put it on the disk very carefully. So this part, red part goes to this part, and the green part also sent to this part. I will denote it by F. This is my. So what is map F? F is from the, you start from the unit rectangle. So first contract and expand, banding, put it on. This is the map F, the diffeomorphic way. So we don't need the exact formula, just the diffeomorphic way we can construct the F again from the unit disk, contracting, expanding, banding, put it on. This is the function F. It looks very simple. And then we extend the map on the sphere, the compact smooth manifold, like this. Here n is a north pole 001, n is a fixed point. And if you take a point x in the southern northern hemisphere here, so we can identify D with the unit disk, unit scale. The unit scale. Already we have the unit scale. We can identify with the D with the unit scale. And if you take a point x in the northern hemisphere, except n, if sufficiently large n, Fn, arrive in here, back to disk, back to the unit scale. This is the dynamical, this is the flow. So if you take a point in northern hemisphere, then after sometimes arrive belong to the southern hemisphere, then from here already we have the dynamical sum F. Contracting, expanding, banding, put it on. That is the dynamical system. We can make F. F is a homeomorphism. So the diffeomorphism. So the diffeomorphism F on the unit sphere S2 defined as what is called the Smale's horseshoe, right horseshoe, contracting, expanding, banding, put it on. Just we have two actions. contraction and expanding. Then what is the dynamics of a horse-male's horseshoe? That is, which point are periodic, which points are non-wandering, which point are chain recurrent. You can imagine on the sphere, unit sphere, southern hemisphere is a disk. You can imagine that is a unit scale, contracting, expanding, bending. Northern hemisphere dynamics is very simple, but southern hemisphere very complicated. We cannot imagine which point is periodic, which point is non-wandering, which point is a chain recurrent. So dynamics looks very complicated. Surprisingly, Steve Smale used the symbolic dynamics to understand the whole dynamics of the horseshoe. Before that, let me introduce what is the non-wandering and the chain recurrent quickly. We say that a point is non-wandering if for any neighborhood u of x and time t, there is a small t bigger than or equal to t capital T, such that T of u and u is intersect. If a point is met again, then is periodic. Non-wandering means the point for any neighborhood. If you take a small neighborhood again touch, that is non-wandering. Let me show you that if you take a neighborhood of x for any neighborhood, any small neighborhood, then after t second, the neighborhood touch like this. In this case, we say that the point x is non-wandering. I'm going to denote omega of phi is the set of all non-wandering points of phi dynamical systems. One more definition, we say that a point is a chain recurrent if for any epsilon there is a there's a periodic epsilon pseudo orbit through the point x. Pseudo means distance between phi ti of xi and xi plus 1 is less than epsilon. In my yesterday lecture, I explained about the pseudo orbit. Pseudo orbit corresponds to the numerical solution in ODE or PDE. So by figure, I'm going to explain. So here, point x0 equal xn. So pair is a pseudo orbit implies this point after t0 second arrive at here. After t0 second. And in the epsilon neighborhood, we can take x1 here. And after t1 second, arrive at here. After t1 second, arrive at here. We choose again x2. After t2 second, arrive here. So we can take x3 inside in here. And so on. And finally, xn minus 1. After tn minus 1 second, arrive at here. And the distance is less than epsilon. So this is the periodic epsilon pseudo orbit. It's not a real orbit. It's a pseudo orbit. Allow the epsilon error. We allow the error. This is the periodic epsilon pseudo orbit. So x is a chain recurrent implies for any epsilon. If there is a periodic epsilon pseudo orbit through the point x, through means x0 equal x, xn is equal to x. In the case, we say that x is chain recurrent. Also, I'm going to denote it by CR of phi is the set of chain recurrent point of phi. Using this terminology, we are going to investigate the dynamics of a Small's horseshoe again. For convenience, I am going to denote dn by intersection from I equal to minus n to I n fi of d for every n. So d1 is f minus 1 of d intersection d. D was the unit square. What is f of t? F of d is, you can imagine again, contract, expand, bending, put it on. That was f of d. Let me show you the figure. Here's the d. F1 of f of d is this one, right? You can imagine. Then you can imagine what is f inverse of d. This is f inverse of d. So intersection disk, the square, unit square, intersection d intersection f d intersection f inverse. This one is d1. Then what is f2, d2? What is d2? D2 is f minus 2d intersection f minus 1 d2 intersection d intersection f of d intersection f2 of d. So what is the, you can imagine. In the previous figure, again, contract, expand, put it on the unit square. Can you imagine the figure? This, again, this is the f2 of d, right? And f minus 2 of d. And the d intersection, d is 16th rectangle. Length is 1 over 25. This is d2. So you can imagine d3. What is d3? Again, contracting, expanding, bending, put it on, intersection. Can you imagine that? What is dn? We are going to put lambda is the limit of dn. We have the limit. dn is compact and the intersection properties, finite intersection properties. So limit lambda is here. Lambda is intersection with dn. Then what is lambda? You can imagine lambda is hyperbolic. You can imagine because lambda belongs to the unit square. In this part only, contracting and expanding. Contracting and expanding. So there is a contracting part and the expanding part. So we can easily understand that lambda is hyperbolic. But it was a discrete dynamical system, so we can consider its suspension flow. From the discrete dynamical system, we can make the continuous dynamical system by the suspension technique. Then the suspension flow is hyperbolic also. Surprisingly, Neil used the symbolic dynamics to understand the dynamics of the horseshoe on lambda. And he proved that this dynamical system on lambda is invariant. Lambda is compact invariant set. This is conjugate to the shift map. Here, sigma is a shift map from sigma 2 to sigma 2. Sigma 2 is the what? 0, 1, for example, 2 symbols to the z. With the product topology, you know the shift map, left shift, one shift map. Smell proved that they are conjugate. Conjugate means two dynamical systems are exactly the same. Topology conjugate means dynamical system of F and dynamical system sigma exactly the same. In the, for example, two topological spaces are homeomorphic. Then we do not distinguish between two spaces in the sense of topology. Two dynamical systems are conjugate, topological conjugate. Then we do not distinguish between two dynamical systems from the dynamical point of view. So if there is a periodic point, then corresponding point is periodic. Non-wandering point to go to non-wandering, chain recurrent point to go to chain recurrent. All dynamics are same. So surprisingly, Smale proved that horseshoe map is topologically conjugate to shift map. So we know the dynamics of shift map. For example, for any natural number, there is a period point, xn, whose period is n. For the shift map, we can prove it easily. But for the horseshoe map, almost that is impossible. But they are conjugate. We can say that for any natural number also, in the horseshoe map, there is a period point whose period is n. Also, lambda is topologically transitive. It means there is a point whose orbit is dense in here. Moreover, period points are dense in lambda. We can easily show that for the case of shift map. There are many. We know that for every natural number, there is a periodic point whose period is n, and the periodic points are dense in here. So for the case of Smale's horseshoe map also, every periodic points are dense, we can say, and the non-wandering set equal to chain recurrent set, all the equal to, because that is dense in here, so that is a lambda. We can see that. So every point is non-wandering point, and every point is a chain recurrent point. So that was the example of a hyperbolic set, Smale horseshoe. So in differential dynamical system theory, the hyperbolic set has the following properties. First one is hyperbolic set. If lambda is hyperbolic, then it has the expansive property, also shadowing property, also structural stability property. And also there are a lot of dynamical properties are satisfied. So in the case of hyperbolic dynamics of hyperbolic set is very well understood. Very well understood. First one is expansivity. More precisely, if lambda is hyperbolic for a flow or compact smooth manifold, then the flow is expansive on a neighborhood U of lambda. It means in a small neighborhood of lambda. For any epsilon, there is delta, dynamic delta ball. For every point x in U, dynamic delta ball is contained in orbit arc. In my yesterday lecture, I explained the dynamic delta ball is what? Dynamic delta ball axis go together. Y, the point Z, Y go together. What is C? C is a control speed function. The speed Y is very fast. By C, we can control for some C, just continuous function. So we can control the speed. So dynamic delta ball is contained orbit arc. If lambda is hyperbolic, that is true. Also, if lambda is hyperbolic, then phi has the shadowing property of lambda. This is so-called shadowing lemma. It's very famous shadowing lemma proved by many people. It means for any epsilon, there is delta such that any delta should orbit psi in lambda. That is epsilon shadowed by a point. It means lambda is here. If you take a delta pseudo orbit, nearby there is a real orbit. That is a shadowing property. If lambda is hyperbolic, then it also has the shadowing property. And also, important property of the high probability structure is structural stability. If a whole manifold is high probability, so anosoph, then that is structurally stable. What is the meaning of structurally stable? There exists a C1 neighborhood of the flow or vector field such that every psi in the neighborhood is topologically conjugate to phi. This means mathematically there exists a homeomorphism and the continuous map such that alpha is a homeomorphism such that H this one. It means, again, a dynamic on the manifold. Dynamical system is a phi is structurally stable. Implies under C1 perturbation. We have here original system phi. Here is the perturbed system psi. Under the C1 small perturbation, dynamics of the original system and the dynamics of the perturbed system are same. We cannot distinguish. They are topologically conjugate. Topological conjugate means dynamics are preserved. Dynamics of the original system send to dynamics of the perturbed system. Dynamics of the perturbed system send to dynamics of the original system. So if the system is structurally stable, then under the C1 perturbation here, not C0 perturbation, C1 perturbation, dynamics is not changed. In the case we say that the system is structurally stable. The theorem implies the whole manifold is high probability. Then the system is structurally stable. Let me explain by picture again. Okay, here is the original dynamical system. This one is the perturbed system. And if you take a point X and the orbit in here, then we can take a homeomorphism H here. Then Hx in here. Then we have the orbit. We have the orbit of psi. Then H send to this orbit to this orbit. But here, important thing is here after t second arrive at here. But here, not t second. Control the speed. Alpha is a speed control function. Depend on x and the time t. Speed control function after alpha of x t second arrive at here. So this is the point psi of at this point. After this second arrive at this point. Then by h, this point send to this point. That is, they are equal. So dynamics of this one and the dynamics of perturbed system is not changed. In the case we say that structure is stable. In the theory of dynamical systems, when the system is structurally stable, is one of the very fundamental and important problems. In other subject also, stability problem is important question. And the original system is here, and the small perturbation, sometimes C1 perturbation, sometimes repeat perturbation. Under the small perturbation, how much dynamics are changed or not changed? If not changed, that is structurally stable. But important thing is here, under the C1 perturbation, not C2 perturbation, not C1 perturbation, C0 perturbation. So here is a very important, it was a conjecture, long time standing conjecture, more than 20 years. It was a long time standing conjecture, but it was proved by many people. So it is a theorem. It was a conjecture, C1 stability conjecture, but it is theorem nowadays. Theorem implies C1 flow is structurally stable if and only if It is satisfied axiom A and the strong transversality condition. We do not know what is axiom A and the strong transversality condition. This is the dynamics on tangent bundle. Structural stability is the dynamics on the manifold. In the small perturbation, dynamics is not changed. So it's the dynamics on the manifold. The axiom A property is dynamics on the tangent bundle. Strong transversality condition is also dynamics on the tangent bundle in some sense. So it is very proved many by Robinson. Robinson proved Clark-Robinson here. Robinson means Clark-Robinson. Proved that axiom A plus strong transversality condition implies the structure stable. The converse is very difficult. For the case of a discrete diffeomorphism case proved by Manne, and for the vector field case, flow case, after 10 years, Manne, after proving the stability conjecture for diffeomorphism, after 10 years, Hayashi proved that for the flow case. Okay. So let me give you the notion of axiom A and the strong transversality condition. Okay. We say that a flow P has the axiom A. First, non-ordering set is equal to the close of the periodic points, close of the periodic set. And non-ordering set is hyperbolic. In this case, we say that phi dynamism satisfied axiom A. Stable manifold theorem says, if phi satisfies axiom A, then for any point in non-ordering set, the stable set, this is the set of y such that the distance between 2 points go to 0 as t goes to infinity. Unstable set is the set of y such that the distance goes to 0 as t goes to minus infinity. Stable manifold theorem says that the sets are C1 immersed submanifold of the M. In the local stable set, they are C1 embedded in the global stable set, unstable set, C1 immersed submanifold of M. Now we suppose the flow satisfies axiom A. In the case, we say that phi has a strong transversality condition. It means for any 2 point in non-ordering set, stable manifold of the orbit of P and the unstable manifold of orbit of Q, they meet the transversal way, not tangent way, not this way, not this way, transversal way. So many two, so manifold meet the transversal. Transversality implied means for any point, if they do not intersect, doesn't matter. But if they intersect, if they meet at x, the tangent space of M at x is the tangent space of the manifold, stable manifold, and the tangent space of the unstable manifold. They are. So in this way, if they meet, then it's okay. So axiom A plus strong transversality condition implies structurally stable. Conversely, structural stability implies axiom A plus strong stability conditions. It was a stability conjecture, but it is proved. So it is a theorem. Let me give you one application of the structural stability. Consider a Chaffee-Infante equation given by this one. Omega is a 0 pi, f is a seed function, and the derivative is bounded for some. This is dissipative condition for the well-posedness. Then it is well-known the system equation induces a dynamical system. on H01 space, H01 of omega 0. And the dynamical system admits a global attractor. Global attractor is unique. What is global attractor? On the phase space, it is a compact invariant set such that which attract all bounded set to here. All bounded set. If there is a bounded set, then attract. That is a global attractor. So every dynamics contained in the global attractor. It is well known that if lambda doesn't belong to 1 to the 2 to the 2, then it is well known also. The dynamics admit finitely many equilibria which are hyperbolic. Also, dynamical system T0 satisfy the strong transversality condition. Finally, we see that the dynamical system T0 induced by Chaffee-Infante equation is structurally stable on its global attractor. Under small C1 perturbation, non-linear path, small C1 perturbation, dynamics are not changed on the global attractor. They are structurally stable. Finally, let me introduce one conjecture for this. Let me introduce some terminology. We say that an invariant set is C1 robustly something P. P can be expansive, robustly C1 robustly expansive, C1 robustly shadowable, C1 robustly transitive, C1 robustly transient, etc. And C1 robustly P means if there exists a C1 neighborhood U of X and the neighborhood U of lambda such that for any Y in UX, lambda Y, what is lambda Y? Is the maximal invariant set in U, has the property P. In this case, we say that lambda is C1 robustly P. Again, the chain component is the, chain component. I will not give the detailed definition again. The chain component is said to be C1 robust shadowing. If there is a C1 neighborhood UX of X and the neighborhood U of gamma such that for any vector field in the neighborhood of X, Cy of gamma Y is shadowable for Yt. Yt is a flow dynamic induced by Y, where gamma Y is a continuation of gamma. Gamma is a periodic, hyperperiodic orbit. Gamma on the perturbation, this one is also periodic orbit. So under this terminology, I am going to introduce one conjecture. I tried to prove this conjecture problems for a couple of years, but I failed. So I hope if someone has an idea, it would be highly appreciated. Please contact me. Let X be a C1 vector field on the compact smooth manifold, and gamma is a hyperperiod of Xt. The assumption is if the chain component is robustly shadowing, then it does not contain a singularity. This is the key point. In the theory of differential dynamical system or continuous dynamical system, singularity always make us difficult problems. Near the singularity, very complicated and not easy to control the dynamics. We proved that. If chain component is robustly shadowable, then it does not contain a hyperbolic singularity. We proved it. But still, we don't know. It contains non-singular hyperbolicity or not. If it is true, then the set is hyperbolic. So I tried to prove this problem, I strongly believe, does not contain singularity. If that is in the small perturbation, that is also has the shadowing property. I believe that is does not contain singularity. Finally, let me introduce 3 books for differential dynamical systems. First one is written by Jacob Parles and De Mello. The title is Geometric Theory of Dynamical Systems. Second book is Schub, The Global Stability of Dynamical Systems. Final book is not book, it's a paper. The Steve Smale, Differential Dynamical Systems, published in Britain, American Mathematical Society. Okay, thank you for listening. This is the end of my talk. Thank you.
Thank you very much, Professor Lee, for an interesting lecture. However, we have a question from our audience, and the question is, what definition of a quasi-periodic orbit seems to you the most constructive? What numerical criteria can be used to separate them from the rest?
Quasi-periodic orbits is first periodic pseudo orbit. You mean the periodic epsilon pseudo orbit? I'm sorry. What is your question?
The question is, what definition of a quasi-periodic orbit seems to be the most constructive?
Yes, periodic, periodic epsilon pseudo orbit means here. So we allow the error. Real orbit is one function, or the solution curve of the differential equations. But pseudo orbit is a numerical solution of the differential equations. You can imagine like that. Then periodic pseudo orbit means periodic numerical solution. So we allow error in here. For example, periodic means x equal to x. Starting point is x0 equal to x, and the ending point is xn equal to x. So it is periodic, but we allow error, epsilon error. So after t1 second, epsilon error, we allow uniform epsilon error. In this case, in the theory of dynamical systems, we say that that is a periodic epsilon pseudo orbit through the point x. Okay, any other questions?
Thank you very much. However, there are no questions for now.
Excuse me, do you hear me?
Yes, I can hear you.
But you did not directly answer a question about quasi-periodic.
Quasi-periodic. You are talking about quasi.
He asked for almost periodic. Almost periodic.
Almost periodic. And there are many different, depend on the book or literature, or paper. Someone use quasi-periodic in this way. Someone use almost periodic in this way, different way. So yeah, I don't know. Yes. Okay. So sometimes, yeah, depending on the non-wandering point. Non-wandering point is sometimes someone say that is quasi-periodic because periodic means the point, the starting point, and the ending point touch. That is periodic. And non-wandering means for any small neighborhood, after some second, touch the neighborhood. What is the chain recurrent? Means not exact orbit. Should orbit touch? So there are many should periodic, quasi-periodic, almost periodic. So depend on the literature or person, I'd like to say. Okay, sorry.
Thank you very much, Professor Lee.
Thank you for listening. Again.
That's all for now for questions. And we can have a rest for 10 minutes till the next lecture.
Dear listeners, we continue our online international workshop, and our next lecture is Professor of Heidelberg University, Willie Yeager. He will continue his course of lectures called Can Mathematics Help to Understand and Control COVID-19? And I want to pay attention that if you have questions during the lecture, you can write them in questions and answers. We will read them at the end of the lecture and try to answer. Professor Jäger, you're welcome.
Can you see the screen, my slides?
Yeah, we can see
Okay,
it, but could you share? Yeah, great.
Now I wanted to see if everything is okay.
Yeah.
Now I planned these 3 lectures in order to motivate mathematicians, especially the young ones, to take part in the fight of science for helping to overcome this terrible situation which we have. And I think it's more and more mathematics needed. In fact, if you listen, I listened this morning the news, they make statements, people from all over the site, which as soon as it gets quantitative and needs information about what has to be done, it's needed. Mathematics combined with knowledge in all the fields, which essentially is, in this case, you have to understand topics in medicine and biology, but also since it's a social event, such a pandemic, we also have to get involved how to introduce in all our models, if it's possible, also the reactions of the population, of the individuals. We had in the last 3 lectures, 2 lectures, we were considering the action of the virus inside the cells on the micro level, and we also have studied what happens on the body side, and now we are looking the interactions of the different agents in a population, and I think which is absolutely necessary to bridge this information between these totally different situations, because if you look inside a body, you have the individuals, and in an individual you have to study how the virus is acting. Especially what is important for the spread is also the multiplication of the virus inside the system. That means it attacks, as we discussed, starting from the lung and spreads all over the body, and we have to understand that and how the body reacts, because one very important topic which is mostly neglected up to now is a period after the infection, where if a individuum is infected, it may show no signs, it may not react, it may react, and we have some uncertainties in this very, very important topic, namely, when does this person who got infected gets himself or herself again as infectors. And I called this yesterday, the virus is a hidden virus and not predictable. All these situations are very uncertain, and we have to handle that. It's clear, not just with simple systems, because a lot of them is also stochastic inside. And what I want to, we had that yesterday already in the discussion. I think if you look at the models which I will show, which are on the market in the following sense, they are used by our governments and by the institutions who make recommendations. Where is the large deficits? And this is more, sorry to say that, I have to more report about deficits than what is really actively really helpful. And one part is just this period. If a single individual is infected by a virus, when does it start to be infective again? Because that's the latency period. It goes from 1 day to 14 days or even longer. But it introduces automatically a time-dependent situation. We have to have functionals there. It's not possible to just to do it as if it would happen just in the next moment. And if you look at the equations, no time lags, nothing in it. There are some few ansatz for that, but it's more from the mathematics side. And there, if you look at that, they are not so much working really in the on modeling the epidemics. I recently had, for instance, to evaluate a paper with 3 diffusion and reaction equation, which takes such kind of reactions inside the body into account, but it's not possible because it's too simple. You cannot use this kind of equations, such simple equation to look at the expansion of such a disease like COVID-19. What is also very, very important, because all these infections, spreading of infections are not just in the empty space. There are measurement, there are interventions done, not just at the moment, not so much by drugs, because we have not yet, there are some drugs interventions. They are very doubtful. They can help sometimes that people get faster healthy again, but really that it destroys the virus infection in a body. It's very doubtful. But we also have not yet vaccines. We have not yet medicaments which are really good enough. And there we have to study this, although based on the knowledge of what happens inside our body. But then we have another problem. Even if you know what is inside the problem, happening in an individual, we have to transfer this information to a population. And we discussed that already yesterday. It's very important to analyze this upscaling. And you must not be astonished if you go from individual agents and try to get up to a particle system, an agent system of agents and agents of different structures. Then you end up with effective equations which are not looking like where you started from. They may end up with functional differential equations. If you are working in these fields, you know that the corresponding stochastic processes behind have no generators which lead just all together to a normal differential equations. And therefore, there's a lot of open work to be done. Another thing is the tests. Also, the tests are very much, and the interventions according to the test are very much a tool to control the epidemics. And there I want to stress once more, the tests at the moment are not what I would like to have, because it tests usually, mostly, very often, mostly the antibodies. That means the reaction of the B cells and the T cells together to an infection. And if they have the correct antibodies which fit to the CoV-2 virus, then you are satisfied. But it's very indirect things. And I had very good relations to discussions with the companies producing those things. And I warned them they should go more for a direct, that means the antigens, the antigens, or directly the virus. But the problem is to identify the virus it's not so easy and costs a lot of money and takes time, because all interventions of a test size have to be global. That means the whole population and hopefully at the same time, because you only can help to intervene with the pandemic if you do it synchronized, because otherwise you have no control how it goes on, especially if that we know that we have this crazy event of superinfectors. Now let me go directly to the text that was just for the connection. I show you here something you might be astonished in the text, if you can read it already. It goes back to 2002. Why to 2002? Because there we had the SARS infection, which is our COVID virus is coming from SARS, but it's more, I'm sorry to say that, it's more terrible. You see on the left-hand side, we discuss it later, you see the development in Wuhan, and you can see Wuhan in its dark red, and in Italy and New York City, which was the first event, the first breakout in the United States. And it also shows you in the vertical line, you have the different kind of where you have lockdowns and where you have social distancing in US, and you also have a stay at home in New York City. And this shows the evolution in these regions. And what is very interesting is that the Chinese really kept down very soon, whereas the others did not get so far under control, this pandemic. But I quoted this from 2002. It's a quote done by Andrew Haldane. He is one of the important bank managers of England at that time. He was there, and he gave a lecture on this event, comparing it with which you find down on the lower part of this slide, on this event which we had in the finance world. And I think why I mention this, because there is always to be seen those modeling which we do for the spread of epidemics is very much connected to other events, in which we are familiar with in finance. And in fact, this lecture I really recommend, because he gave advice to the finance people: look at the mathematical modeling of epidemical spread of epidemics, because a lot of them we can learn for the epidemics in finance, and these networks are very similar, and therefore I wanted to mention this here, because we need it now too, because our looking at the financial situation and the economic situation is really a catastrophe in some countries, and it also influences the spread of the disease, because the people cannot hold what they have to do on the economic and private side, because it's very important, it's closely connected. But that's why I go on directly to the lecture. The sketch of the general structure of an epidemic. We have hosts population, we have a virus population. Both are structured population described by discrete or continuous distributed state variables. I wrote down the state variables. I refer to the profile of the virus, because these models have to somehow contain the features of the virus. Both populations are moving in space and time, and have to undergo birth and death controls processes. Some other models, I mentioned this, don't use this, but we have to have this. The virus particles can be in the host body or outside, but reproduce only host cells in the host cells, causing damages in the host. Transfer of virus between the host occurs by direct or indirect contagious contacts. The transfer from a given exposed host is only possible after latency time, depending on the internal dynamics inside the host, where the internal defense system, we have two, you should be aware of this, innate and adaptive immune system are started. The adaptive immune system is essentially interesting because it adapts to the virus, produces the antibodies. And there I want to say this is not good enough developed, I claim. Also from the mathematical point of view, I mentioned that already yesterday, that George Bell did a very great contribution to it, but it's time to get interested again. So now, here I just show you this trivial picture, which you find also in Wikipedia, where you can see how, for instance, vaccination can help to control some virus. And I also show you that because some people, because you have non-immunized people, you have immunized people and not immunized people who are sick and contagious. And if you by simple playing, you can easily see how they affect the dynamics of the population. Why I mentioned this here is not only because of vaccination, but there is the idea of some of our colleagues also put in mathematics that we can use the generation of herd immunity in order to control these epidemics. And but we will discuss it later. The infection is with respect to a host and to a virus population interacting multi-agent system. Due to different scales for host and virus, one has two scales with respect to the population in size and the number of agents. It makes sense in modeling to pass to the concentrations for the virus or later also to the human population in some situations. Mathematically, we are confronted with coupling scales also if are mainly interested in growth and spread of the epidemic on the macro level. Most processes are stochastic and not just deterministic. Multi-scale limits will not produce just differential equations that I said already before. Okay, let's go on. What comes next? Oh, let me just start immediately. Most of these available systems for modeling the epidemics go back essentially to the SIR model. It's an old model of Carmack-McKendrick, 1927-32. And I think this is no longer possible to use, but most of them are just adding some additional terms. The original one you see up there as a SIR model, and SEIR model is, for instance, used by a little bit generalized of that, is used by an institution which takes care in Germany of the evolution and for the advice of the government. And they have to be changed because it's not good enough. And it was known already last century. I've referred to the books and of Enzo Carbasso, who criticized this approach, because the main thing which is the case is that this is essentially system I times S, because it assumes a very trivial reaction time, change, infection influence on the susceptible. It's just a product of I times S, which is absolutely outdated to use it, and you cannot, I think, it's not possible to do that. Let me look at, again, I show you just, I put down already yesterday, we have a whole list of properties of the virus, which we somehow have to take care of in our modeling of the epidemics. And it's also clear it has to have a structured population. It must lead us finally to structured population, for instance, by age or health history, and also we have to see that effects like super spreading have to be taken care of, or the incubation time and the duration of infectivity. Also, what is very important, we do not know very much about the very well yesterday because of time problems, but knowing the immunity, how long does it keep, or is there immune memory to vaccines, and how long does it hold? It's a very important topic for modeling the spread of the epidemics. Now I give you something which I was very surprised. What you see, first of all, one of the most important is Johns Hopkins University in this studying the epidemics, because they are collecting all data all over the world. I hope you had the chance to look at this data from day to day. And I use this too. But they produced in 2019 an index which was designed to just read the last part on the slide. The GAs with poor measurable changes in national health security and improve international capability to address one of the world's most omnipresent risks: infectious disease outbreaks that can lead to international epidemics and pandemics. 2019, they showed us who are best prepared. I show you next page. And the colors you see, what they mean, you see it's very small. You see it here, what it means. The yellow ones are very well prepared. The in between color is more prepared and least prepared. And look at this, what do you see already? Yellow is almost all part of North America. And maybe if you go to Greenland and go to Canada, this might be okay. But look the evolution in United States. Now I put you here the ratings, and you may look, I could not put all of them. The ratings, your top rated is United States, United Kingdom, Netherlands, and Sweden, also higher. Germany is lower down. Italy is also quite back, but China and Russia are very terrible. Especially Russia is far back, according to this index. And I never believe indices very much, but there we have it. It's not uninfluential to have this. Now, look at this. How do you compare globally? You find here listed, according to the situation of the 2nd of August, the different countries, how much they have. And in the meantime, we have about 5 million more globally of infected. And you see, please look at the rank, which is the last part, and there you have the ranking. USA was #1. But they are also #1 in the pandemic. And in the bracket, you see the official indices number, which gives you more detailed information. But the same thing is USA. And also Brazil was quite good, well rated by this. But they are leading. And Mexico and UK and Spain and Italy. You can compare how terrible this is fitting to the real life situation. But we may need such indices, but you have to look very critical at them. Now, let me just, I also want to say the following. If you want to compare different countries, it's not so easy. Now I show you the evolution of in the last time of the pandemic in United States, and it was provided by New York Times. Also, you could have gotten this, can get this movie there, and if you have a chance, how to load it down. But maybe I could start it once more, that you see that my statement, no, it does. Now it repeats it once more. Now you see it once more. I doubt that you can describe it by this spread of the epidemics by a diffusion equation. It's not possible. It's clear why. Because commuting of people is very important. It's clear. You have to know where the centers are of this country, and you have to study very carefully how the commuting is. And we know this already from HIV virus, that a single staff member of an airplane transported HIV to California. And it's in the meantime we can follow, and it was also done studies to identify the evolution of single infectors for instance, in Germany. They traced it very carefully. Now let me continue. So, urgently required orientation in situation of uncertainty about the virus and infection, meaningful decisions on how to act in this pandemic, and this cannot be done without mathematical modeling and simulation, because you have to see the effect at least in a digital scenario computation. How is the virus spreading in the body is necessary, and how to stop it to spread. Mathematical modeling and mathematics itself is needed. And in Germany, it's mainly done by an institute, Robert Koch Institute. Robert Koch is very famous in epidemiology and in infectiology. He was a famous physician and microbiologist. And he said the following: the question is too good to spoil it with an answer. I apply to this situation. We have really urgent questions, but these questions are too important and too good to give bad answers, which we get at the moment. Answers to our question by RKA based, by the Robert Koch Institute, are based on investigation of the Helmholtz Center and in Braunschweig, and they use essentially also. I show you their model, and they used all these factors R0. The R0 factor I never understood before, because how can a single number decide on the asymptotic behavior of a complex system? It's impossible. But they never told you what models they use. And the models are essentially simplified, a simple generalization of the SIR model. And I quote here what they say: mathematical models of viral epidemics are well established. R0 is a basic reproduction number which informs about the average number of persons infected by one infected individual. It can be calculated from the parameters of the respective model. That's what they write. I think that's not true. For their specific models, yes, but I cannot talk about that we can handle with any of the existing models our epidemic at the moment in a good way, as we should. A suitable approach to determine R0 in particular regions is to fit the model parameters to registered CoV-2 positive cases over time. The thus produced R0 provides an information over the overall spread of viral dissemination and does not provide information about the effective measures installed in the course. But here we see they tell you you can look afterwards from looking at the situation if these measurements which you took are affected. But this does not give any tool to control it a priori by scenario. Therefore, I cannot accept this approach. Now, there you have the different mitigation measures. You know all of them. I just gave that a picture, and you see all of the. I put on the left-hand side. It was a demonstration in Washington showing how many people and the medical people died, and you have on the right-hand side all these graves in Brasilia. And we have the different medications which are possible. I had told already yesterday about we have an airborne decision, aerosols and droplets, but also we can do it contagious. Let's think about that. And we have different kind of measurements which have to be taken, which are listed here, but they're so familiar with you, we don't have to discuss. Interventions are necessary. Failing to introduce appropriate measures are or to put an end to such measures can lead to humanitarian catastrophe, and that's exactly now in discussion. Now, different scenarios: uncontrolled epidemic with many fatalities and overwhelmed healthcare, long-term ongoing infections treatable with reasonable healthcare, eradication of the acute epidemic. Uncontrolled, that's a lot of people who, those who represent herd immunity set on mainly on A. B is what most do, and C we cannot do without in the situation which we have now. We need better tests, we need some vaccines, and we need medication and a functioning public health system. And really also it must fit the political and social and economic and financial system, as also be stabilized to control that. And I said the concept of herd immunity we have to take into account and discuss. I make some critical remarks. Look at that. I show you UK. It's all data of the 2nd August. UK had infected here 305,000, and I took it per million of inhabitants. That's not correct, because we also would have to look at the density of population, but to get a good measurement for comparing different countries in the epidemic behavior, it's not so easy. But let's just divide by the number of inhabitants, and now you see the situation. UK is not in a good situation, and Sweden also not. Also Netherlands, I didn't put down the figures. And you also see, I gave you the comparison in Germany and USA. And what can you see about UK and Sweden? They had this herd community as a philosophy. And I'm sorry to say that also supported by some of our mathematicians, mathematics models, which reminded me already what happened already in UK with the crazy cow disease, because they also used the wrong model at that time in the government, because they liked the outcome, and it had to be corrected. And I think UK tried to correct it, and Sweden claims that they are successful, but look at the situation. It's not true. I think that this okay. Here you have once more the herd definition of the herd immunity. Is a level of population immunity such that disease spreading will decline and stop even without preventive measures. When the immunity level from infection is below the herd immunity level and preventive measures are lifted, then a second wave of infection may start. But they claim we can reach this herd immunity. The phenomenon of herd immunity is complex. The simple crude threshold theory, it is the basic model for the interaction of transmission and immunity threshold, is naive because it is based on a number of assumptions that are not given in reality and on factors that are not yet sufficiently understood or quantifiable or are still unknown. Strategy to keep the healthcare functional and to delay viral spreading until parts of our immune, this strategy will fail, and it has been shown already. And we look in China, there you could see that you can get 1% immunity by this way. So now what do we have as next? Oh, maybe I said already most of this. I can let it for time reasons. Let me show you the system used by the Helmholtz Center for infectiology, and it's based, all German predictions are based on this model. And you see already that it's a simple generalization of SIR model. They just introduce some additional subpopulations, but this is the criticism which I said before works here immediately. And I show you some of the results. They have this kind of differential equation, and here they give you exactly the R0. If you know these parameters, you can compute this. It's a little bit funny that you can get from the asymptotic behavior just by one single number in the parameter space. Usually you would say they have certain regions, which, but not just given the parameter that it's that this only figure decides where it goes. It's a specific situation, and not, I think it doesn't hold for the. And now you see on the left-hand side, they did some computations, but not so much for the future, but they explain that what has happened because they have no modeling how this develops in the future in this case. But they extrapolated later knowing, assuming the R0s, relations on the R0s. Here you have the evolution of in Germany in this period, and here you have. They also computed their R0, but the R0 they let it depend on time because they had to adjust it because it changes. But they took a certain period, a certain window where they computed for each window the RT, and then you have a time-dependent case. Now I have to be a little bit faster. And here they also looked at Germany and a certain evolution for a longer period, no? And but under certain restrictions on R0, they took this the time-dependent reproduction factors from the other parts, and then they took perturbation and looked what happens in the future. But if you would rely your decision on some pictures, it's your problem. I wouldn't rely on that. Critical comments. The model system has a structure that a single number given by a function of its parameter determines the asymptotic behavior. A SIR model is generalized too simplistically. We has long been known to be unsuitable for infections, and for more suitable models can be expected that the corresponding parameter H can be described by graphs of functions. Singular. A modeling system does not offer direct links to possible control measures. There is no spatial growth and spread, insufficient state structure in the human population. Random processes play an important role, and they are partially touched by the Helmholtz Center, but in general not. No. Now let me look at, oh, excuse me. This is I want to show you. You have on the left-hand side the SIR model, but already shortly in the last century in the 90s, Capasso mentioned we should replace this simple model by a more general model, where GI is a nonlinear function, and in fact this is necessary to do. And then you see different kinds of choice of these nonlinearities, and they have a different give a different asymptotic behavior. I give you some examples of these G's, which you see. It's a Holling type, and in Holling type you have two parameters. You set all these two parameters equal, and then you have different kind of asymptotic behavior, which really are important to have that, and very much how this function will look like. We know what we have to expect for the dynamics. I give you another argument, which I think it's necessary to see, is the following. We discussed a system of ordinary differential equations, coupled chemostats, and take instead of chemostats cities, for instance, where you have inside going on the epidemics. Here is fighting for food in that. And if you use Michaelis-Menten kinetics, you get such simple systems. And you have n species and n species and n vessels. And the problem is asymptotic behavior of such things, because they are really complicated. I skip this at the moment. If you are interested, I can tell you where you can find it, but I show you just the result. You see, you have three species and three vessels. And you can show in a system of three species under for this kind of equations, at most, generically, at most three can survive together. And you find it up there. Now you ask what happens. If you perturbate, and you see small perturbation give a little bit difference, but a larger perturbation of only one parameter, because of the nonlinear Michaelis-Menten kinetic, you just took one parameter. Look at this crazy behavior of this dynamics, and this is, I think we have to take this into account. We have nonlinear situation, and this may be in certain regimes very getting to crazy dynamics too, and we have to take care of it. There has been also SIR model for generalized SIR model for the evolution in China. They also introduced one additional situation that they do not know all they differentiate between recovered and not recovered populations parts, and they get then the following kind of results. And they now see if they keep their information for if they go back in the history and only take data up to January, then they are not so they are not so good. And if they go data up to March, then they are really good to identify the evolution of the epidemics. It's a little bit like that. You generate with your models enough functions in order to give a good approximation of what you know anyhow, but the prediction for the future is impossible. There also has been a recent, all these are recent contribution. You see, this is from the 23rd of, published 23rd of June, and this is one representative of the herd immunity. Generalizes a little bit better the system, and but it's essentially SIR model, and again, what you get it's not reliable. It's a very trivial thing. Their contribution is, can the herd immunity, if it exists in the sense that they mean, be influenced by the heterogeneity of the population. They were interested in the heterogeneity population, and they did not take a continuously distributed but a normal one. Now let me see, what is necessary? I think it's necessary to replace the systems by modeling modeling the whole agent system on a network, which in each node might be treated in a city. You may be able to treat it like traditionally, but if you combine different regions and city, you have to do these network studies, and there is a lot of done in physics, because they like to do network studies, reactions on networks, and the simplest one are those coming from epidemics. And I really think that we have to look at it. And they are very similar to the networks which are studied in finance or in social science or internets. And there I see the future to get more precise results. You can maybe replace this network system by integral equations, because you can spread a little bit just the lines connecting to cities, but I doubt that you can do it with a heterogeneous PDE directly. You may in some cases, but that's what I wanted to say here. We also have to get involved in testing and vaccination, and there I think we should be able to use mathematical modeling to make testing better and vaccinations also better, because we have the chance to use what is called in industry partially digital twins. That means you make a model, connect it with a database, and try to adjust your model always to the changing database and compute something as for prediction which you may need for all your measurements. So, can mathematics help to recover from lateral damage of the pandemic? I think yes. And I think it's needed mathematician, in particular of the younger generation, and I think dare to get involved with mathematics in biology and medicine. But you must be willing to accept. You have to find the systems of equations. Their derivation is part of the problem. You have to get to front of biological and medical research in order to be informed about the processes they are supposed to describe. You have to get seriously involved in interdisciplinary research in the challenges posed by COVID-2, threatening humanity as a pandemic and as a virus sepsis. This is very important because sepsis is already studied, although this has no solution yet to control it. And it's worth the effort from all point of view, as mathematics can give decisive contribution to understanding COVID-19 and getting it under control, repairing the damage and caused by the pandemic. Also, we get new mathematical problems which are challenging theoretically very much and can help to develop new interesting mathematics too. So I think this was all what I wanted to say. Sorry. You see, medical people from Wuhan, they already claimed victory. I hope this is true, that there are coming no new waves, and we should try to help to avoid that. Thank you very much for your interest. Stay healthy. And if you have any question, which cannot be posed now because it's too short a time, but if you have, I have enough literature collected because that's our source. We have to study the publications in the field by reliable medical institutions and biological institutions too. Thank you very much.
Professor Jäger, thank you for the interesting lecture. And we have some questions. The first question is, we have the information about population immunity at the moment. Can this information be used for mathematical models? I'm sorry.
I'm sorry, I have to correct you. We don't have this information about immunity. That's wrong. People, you see, if you produce for the moment antibodies which fight the virus, You do not know how good is the memory. In fact, it needs to be studied. And this is why I said the old models which we had I like George Bell very much. He was a good friend of myself, and he contributed so much. But we have to do more study in this immunological topic under the aspect of the coronavirus. If we have it, that's a very important information, but we don't have it.
Okay, and we have one other question. It's just a continue of previous question. Maybe it's not for the strictly answer, but for discussion. The question is, can we fight the virus just having the needed level of population immunity, means without vaccine?
I think we should, first of all, I hope that everyone who says that he can produce a vaccine can produce it. And the more we have of it, the more it's healthy for us. But I am a little bit worried by that some people promise too much. And because if you look at some of the companies producing now these vaccines, some of them have no experience in the treatment of such virus epidemics. Some are coming from cancer, and it's different. In fact, I was involved because I also was asked about suggestions for vaccines. And there are two kinds of vaccines in principle, two kinds. The vaccine is you want to stir the immune systems, the B cells and the T cells, to create antibodies to fight and create a memory that you have been attacked. And you can do it in two ways. One traditional way was produce the vaccine outside of the body. This is the traditional one. And then you have the other one, is you bring in RNA, messenger RNA. Messenger RNA codes a marker, the production of a marker of the virus. But it has only the code. You put it in the body, and in the body the cells start to work on that and produce now markers which initiate, hopefully, all over in each person who is gets his vaccine, the antibody production. This is a complicated process. Whereas the old one, you knew what you did. The new one is new, and I can go back. I can give you Nature articles for the review. When will it work? They said in several years. It was before the COVID. There exists Nature articles about it. It's very complicated, and we only can hope that we get these vaccines. Otherwise, one tool which you have is tests, but not the antibody tests, but the virus test. And this is not very successful yet. It's too costly. I showed you yesterday shortly using light microscopy. You can do it. You can see the virus, but the machines are expensive. If you can reduce it to simple machines, then it's the best way to do that. Again, there mathematics and modeling can help, because maybe you can reduce it. In fact, I discussed this with one of the scientists at the company who produces these antibody tests. I said, it's good now because we don't have anything else which is cheap. You can use it like you did use a test for pregnancy. You can do it at home and you get immediately the answer yourself. But I said, you better should have the virus. But they say, we cannot measure, we cannot produce it in a good strength. And I also said, you spit on that piece of paper and then you see if you have the virus. But they said it's not concentration is too small. We have to use this machinery to multiply the concentration. But now he seems to have a better approach, which makes it possible maybe. This is one thing which we can do, because then we can isolate the infected people. And you see, HIV has no vaccine, but it has good medication and good tests.
Thank you, Professor Jäger. Thank you for your interesting lecture and your answers. We have another questions from our listeners, but unfortunately, due to the schedule, we have to postpone it for discussion in the evening. Thank you once again, and we are looking forward to you in our discussion. And dear listeners, a break is announced until 12 a.m. Moscow time. Thank you very much. Dear listeners, welcome again to our online international workshop. And I would like to present to your attention Professor Galina Lazareva, a professor of Ruden University, and she will give a course called Mathematical Modeling of Compressible Fluids. It's lecture 1, Introduction to Compressible Flow. Dear listeners, I remind you that if you have questions during the lecture, you can write them in questions and answers. We will read them at the end of the lecture. Professor Lazareva, you are welcome.
Hello, dear ladies and gentlemen. Let me introduce myself. My name is Galina Lazareva. I am professor in Ruden University, and I am very pleased to have been invited to speak the online international workshop, differential equations and interdisciplinary investigations. And my mini course is devoted to mathematical modeling of compressible fluids. And today I will tell you about compressible flow. Today I want to tell you about the fundamentals of the mathematical modeling of compressible fluids. A well-known academician Samarsky triad is model, algorithm, and program. And academician from Novosibirsk, Anatoly Nikolaevich Konovalov, expanded this concept as experiment, mathematical model, discrete model, algorithm, program, supercomputer calculations, and then again experiments, and that's all. Computer simulations and mathematical modeling are carried out to understand the results of fundamental physical laws, help interpret experiments, provide detailed information which is difficult to measure, and to design and predict new experiments. I have some experience in modeling processes that are described by systems of gas dynamic and kinetic equations. I achieved some success using the Godunov method, fluid in cells method, kinetic consistent difference scheme, peak method, and SPH method. I prefer to solve multi-scale dynamic problems, taking into account multi-phase, the influence of electric, magnetic, or gravitational fields. Such tasks require calculations on supercomputers. I use importantly to make calculations on the cluster of our university, and I have access to resources of the Lomonosov cluster in Moscow State University. Let's consider the basic concepts of the theory. Gas is the aggregate state of a substance characterized by very weak connections between its components, particles, as well as their high mobility. Ideal gas is gas in which the interaction between molecules and reduced to paired collision and the intermolecular collision time is much shorter average time between collisions. Gas density is the mass of gas particles per unit volume. Excuse me, please, English isn't my native language, so I will speak very slowly. Then a continuous medium is a mechanical system that has an infinite number of internal degrees of freedom. Its motion in space is described by a scalar field density and velocity vector field. Pressure is a physical scalar value describing the state of continuous medium and numerically equal to the force F acting per unit area. The surface S is perpendicular to this surface. And gas dynamic studies the motion of a continuous medium with taking into account compressibility. The thermodynamics and fluid mechanics compressibility are also known as the coefficient of compressibility or isothermal compressibility is a measure of the relative volume change of a fluid or solid as a response to a pressure or mean stress change. In -1 divided on volume multiplied on derivative of volume by pressure. The choice to define compressibility as the negative of the fraction makes compressibility positive in the usual case that an increase in pressure induces a reduction in volume. Same field can behave as compressible and incompressible depending upon flow conditions. Flows in which variations in density are negligible are termed as incompressible flows, and when density variations within a flow are not negligible flow is called compressible. All flows are compressible. Flows are usually treated as being incompressible when the Mach number is less than 1.3. Mach number is the ratio of the speed of the flow to the speed of sound. The most common example of compressible flow concerns is the flow of gases at low velocities, while the flow of liquids may frequently be treated as incompressible under low pressure. If there isn't a significant change in density, then flow as gases can be treated as incompressible. For many liquids, density is only a weak function of temperature. At modest pressures, liquid important.
Professor Lazareva, I'm sorry. Please, could you repeat the last sentence? Due to the network connection, there are some faults.
Okay. Last sentence. At modest pressure, liquids may be considered incompressible. Okay. However, at high pressures, compressibility effects in liquids can be very important. The viscosity of a fluid is measure of its resistance to deformation at a given rate. For liquids, it corresponds to the informal concepts of thickness. For example, syrup of honey has a higher viscosity than water. Then viscosity can be conceptualized as quantifying the internal frictional force that arises between adjacent layers of fluid that are in relative motion. For instance, when a fluid is forced through a tube, it flows more quickly near the tube's axis than near its walls. In such a case, experiments show that some stress, such as a pressure difference between the two ends of the tube, is needed to sustain the flow through the tube. This is because a force is required to overcome the friction between the layers of the fluid which are in relative motion. The strength of this force is proportional to the viscosity. A fluid that has no resistance to shear stress is known as an ideal or inviscid fluid. Zero viscosity is observed only at very low temperatures in superfluids. Otherwise, the second law of thermodynamics requires all fluids to have positive viscosity. Such fluids are technically said to be viscous. A fluid with a high viscosity, such as pitch, may appear to be a solid. The description of gas movement in the framework of the phenomenological approach is connected with the ideas about the average values that characterize its state. When deriving the main equations of the mathematical model, it is postulated that the average volume density, velocity, and other values tend to a certain limit when the volume is pulled to a point. This assumption is justified by the fact that the sizes of volumes containing a sufficiently large number of molecules can be chosen small in comparison with the typical scales of the studied phenomenon. But the small scale movement of a large number the theory
Professor
uses,
Lazareva, I'm sorry, just please repeat the last sentence again. Due to the network fault, we cannot listen.
Mm-hmm. I tell about that this assumption is justified by the fact that the sizes of volumes containing a sufficiently large number of molecules can be chosen small in comparison with the typical scales of the studied phenomena, but the small-scale movement of a large number of molecules within a small volume must also be taken into account in the simulation. The theory uses the approximate description of small-scale processes. This introduces some average parameters that characterize the state of gas. A number of relationships between these parameters are the result of general physical laws. Other relations, equations of state of specific media, arise as a result of generalization of the experiment data. It is known that a gas located in this fixed volume with fixed internal parameters and in the absence of energy exchange with external bodies. After some time, relaxation time comes to an equilibrium state. The smaller the volume, the shorter the relaxation time. Therefore, when modeling processes with a characteristic time of change of average values, much longer relaxation time, it can be assumed that a small volume of gas at each time is in state of equilibrium with fixed external parameters. A continuous change in its main characteristic is interpreted as a quasi-static transition from one equilibrium state to another. Compressible fluid flow is described by a system of partial differential equations. This system of equations consists of three equations. These equations are consequence of conservation laws. A few more definitions for equations. A differential equation is an equation that relates the value of some unknown functions at a certain point and the value of its derivatives of different orders at the same point. And the solution of differential equation is called a function by substituting which the equation becomes an identity. And let's get the continuity equation. Let us select a certain fixed volume V in gas flow. The mass change for the I component in the volume occurs due to the flow or outflow of this component through the surface of the volume. We use the Ostrogradsky-Gauss theorem integral with the volume integral. We get the following equation for the E component in the volume. Since the volume is arbitrary, then we can write this equation, okay? And we will sum up all the volumes and enter the average mass speed. And then we get the continuity equation. Here we see derivative of density by time plus divergence of rho
Блин, тут спросил.
is equal to 0. Let's get the momentum equation. Let's allocate a certain mobile volume V in the gas flow, which moves due to surface forces. The change in the amount of movement, the gas volume, is equal to the sum of the acting surface forces created by the pressure. P is pressure. We introduce the derivative under the sign of the integral, knowing that the mass of the moving volume is fixed. Then we get this equation, and then we use the Ostrogradski-Gauss theorem for surface forces, and we get momentum equation in differential form. We can call it Euler equation. Derivative of momentum by time is equal to divergence of rho v squared plus pressure P. Here, pressure P is a stress tensor. It is the matrix in which the pressure derivative are located on the main diagonal. And this is dyadic tensor. You can say that it is a tensor product of two vectors. It is this is a matrix, all elements of which are velocity derivatives. On the main diagonal of the matrix are the velocity derivatives squares, and other elements are multiplication of derivatives by different coordinates. Let's get the equation of the total energy. Let us again select a fixed volume V and consider the energy balance for it. Rho E is a specific total energy. The energy flow consists of convective energy transfer, rho V E, and the work of surface forces. Conservation laws don't give a closed system of equations, so there is no connection between the total energy rho E and the pressure P. The total energy consists of the internal energy rho epsilon and kinetic energy rho v square. So the total energy consists of internal energy and kinetic energy, and the internal energy is related to the pressure through the equation of state, which for an ideal gas is written as is equal to gamma minus 1 multiplied rho epsilon, where gamma is the adiabatic index. As a result, we got complete system of gas dynamic equation. We get continuity equation for mass, equation of motion of momentum, the equation of total energy, and equation of state. And now let's take a bit of a break from this topic and look at the map of mathematics from Dominic. I like this map. It's interesting plot. On the map, we see everything at once. The foundation mathematics are drawn on the top. The areas of pure mathematics are drawn on the left, and applied mathematics on the right. We'll start with physics, which uses just about everything in the left hand side some degree. Mathematical and theoretical physics has a very close relationship with pure math. Mathematics is also used in the other natural science with mathematical chemistry and biomathematics, which look at loads stuff from modeling molecules, evolutionary biology. Mathematics is also used extensively in engineering. Building things has taken a lot of math since Egyptian and Babylonian times. Very complex electrical systems like airplanes or the power grid use methods in dynamical systems called control theory. And now let's get back to our topic. Now, boundary value problem. A system of differential equations with given linear relations between the values of the desired functions at the edges of the integration. Equations.
Professor Lazareva, I'm sorry. Could you repeat the last sentence, last mind, please?
Boundary value problem. It is a system of differential equations with given linear relations between the values of the desired functions at the edges of the integration interval. This is example of boundary value problem. It is equation of matter transport over the infinite interval here. And the solution of the initial boundary value problem is a function whose substitution in the boundary value problem satisfies the system of differential equations and takes the set values of the edges of the integration interval. For the transport equations at a constant velocity of matter with this formula. Exact solution of the one-dimensional transfer equation like this on a infinite interval has the same structure as our equations. This is the equation of the hyperbolic type. We will talk about them tomorrow in the second lecture of my numerical analysis is a mathematical tool commonly used in places where the mathematics becomes too complex to solve completely. So instead you use lots of simple approximations and combine them all together to get good approximate answers. For example, if you put a circle inside a square, throw darts at it, and then compare the number of darts in the circle and in the square portions, you can approximate the value of number pi. In real-world, numerical analysis is done on huge computers, super computers. Similarly to this example, we will use a discrete model for our calculation. Let's look at the discretization of the calculation area. We select a finite interval from A to B on the infinite x-axis and divide this interval into n equal parts. Thus, a uniform calculation grid with n cells or volumes is introduced. The grid step is divided by h. H is equal to b minus a divided n. Let's move from continuous functions to the discrete analysis, where I, the subscript I, integrates the number of points in the space. Let's clarify the basic concepts of numerical methods. Different schemes, scheme is a finite system of algebraic equations that corresponds to a differential problem containing a differential equation and boundary conditions and or initial distribution. Explain that can be represented as this formula. It means we can immediately find the variables in the next step of time if we knew the previous step of time. And implicit scheme is the scheme that can be represented as this formula. In this case, we will need to find the values of the variables on the new time step in a complex way. To do this, we will need to solve the equation. Maybe you know, for example, the method Dragonka in Russian. Then the scheme is stable if at h, step h, approach 0, there is a sub h. This is our numerical variable. Approach sub h wave. This is our solution. If there is an inequality, you see wave h minus h less than c multiplied h degree n, and we can say that the scheme approximates a differential problem with order n. Now we can see algorithm for solving the initial boundary value problem using an explicit numerical scheme. First, we defining the initial condition for the solution. Then, for each volume according to the numerical scheme, we get the value on the new time step. Then we define the boundary conditions. As an initial condition for solving the problem on the next time layer, we use the solution just obtained by the scheme. And again, let's take a break from our formulas and look at the pictures from Dominic's website. His website has a map of computer science. Here we can see the areas of science that are used in mathematical modeling. Computational science mathematical modeling uses computers to help answer scientific questions from fundamental physics, neuroscience, and often makes the use of supercomputing, which throws the weight of the world's most powerful computers at very large problems, often in the area of simulations. And what did I mention? Computer science. The equations of hydrodynamics are non-linear. This means that only in very rare cases can an analytical solution be found. Thus, the use of numerical methods of solving gas dynamics problems is absolutely necessary. There was a fantastically rapid growth in the speed and memory of computers and the creation of more and more smart algorithms. This led to the rapid development of computational gas dynamics. There are hopes that in the not so distant future, computer calculations will replace expensive experiments in wind tunnels. Today, software for calculation, the flow of liquids and gas, is not only science. This is a commercial product that is actively sold, purchased, and used in many industries. 5 minutes. So the basics of mathematical modeling, compressible. Let's look at the history. In 1917, Richardson first attempt to predict the weather by numerical solution manually with was after the creation of computers, they Neyman and Rickmeyer write an article in which they propose to use explicit viscosity to calculate flows with shock waves. This was the beginning. It was the beginning. This is the beginning of the development of end-to-end counting methods, and I want to tell you about academician Sergei Konstantinovich Godunov. In 1959 was the first open publication of Sergei Konstantinovich with the scheme is based on the solution, the gap A problem. This scheme and its almost innumerable modifications and upgrades have been successfully applied to a huge number of different tasks. It is the basics. It is the basics of almost all modern methods of numerical simulations, shock wave. And in 1983, Harton's article suggests DVD, total variation diminishing schemes. I want to tell you thank you for your attention, and if you like this research topic, you can join our group in European University. We will work together on a thesis and maybe even PhD thesis. Come to my lectures tomorrow. I will talk about hyperbolic equations and their applications. I will tell you how you can predict the result of galaxy collision using mathematics. So, thank you for your attention.
Thank you very much, Professor Lazareva. Thank you for the interesting lecture, and we have some questions. The first of all, the question is, can you explain what is the adiabatic index?
What is the adiabatic index? The adiabatic index. We use here the adiabatic index, and it is the ratio of heat adding during of at constant value. Its value is always greater than 1 because heat added will be more at constant pressure than at constant volume. Okay?
Thank you. The next question is how to set the initial value for calculations.
Initial value. We have algorithm for solving, and first we must define the initial condition. Usually the state of immobility is set, then the initial speed value is equal to 0, and the other parameters can be determined. And sometimes a certain state of a moving gas is known. That's all.
Okay. Another question is, in the case of modeling non-compressible fluids, a system of differential equations appears in which there is a need to study spaces with variable summability indices. What about compressive fluids?
Repeat, please.
In case of modeling non-compressible fluids, a system of differential equations appears in which there is a need to study spaces with variable summability indices. What about compressive fluids? And what spaces appear in this case?
I think we have if I understand you right. I think it is the same.
Okay, maybe we can postpone this question for the discussion part later. And the last question is, generally speaking, is there a complete model of non-compressible fluids in the literature or has not been studied yet? Question, is there or not? Is there a complete model of non-compressible fluids in the literature?
Yes, of course. Non-compressible fluids model described by equations, Navier-Stokes equations, and you can read about it in books, in literature. No problem.
Thank you. And the last question is, why are gas dynamics equations derived from conservation laws?
Yes, we get all our equations from the conservation laws because the laws of conservations are always fulfilled in mechanics. This is sometimes the only thing we knew about a process. Therefore, we can predict the development of the gas flow based on the assumption that at every moment, the time we have energy stored. That's all. And I think that I will definitely read all the questions in chat and tell you more tomorrow at the next lecture of my mini course.
Okay, thank you. I guess everything was clear. Since the audience has no questions, perhaps they will arise in the discussion part in the evening. So, Professor Lazareva, thank you for the interesting lecture and your answers. And we are looking forward to your next lecture tomorrow. And now the break is announced until 1 p.m. Thank you very much.
Thank you. Bye-bye.
Good afternoon, dear colleagues. Professor Walther. Our next lecturer is Hans-Otto Walther, professor of Justus Liebig University of Gießen, with the lecture Differential Equations with State-Dependent Delays, Sound Theory, New Phenomena, and Applications. Professor Walther, can you please share the screen?
I just try to share the screen, but somehow I have a problem and I do not see what goes wrong. Let me try again.
I can see your screen.
You see my screen, the beginning
No,
of my lecture? I don't. Okay.
No, not.
Anyway, then I can begin with the lecture, right?
Yeah, sure. Sorry for some problems. Professor Walther, can you please share the screen again? You are muted. Microphone.
Well, now first, what? Now the microphone should be okay. And now I try to share the screen again.
Mm-hmm.
Okay, now it should be screen number 1. Now can you see it? No,
Yes,
you should be.
I can see it.
It's okay. Okay, then I go to full screen mode.
Mm-hmm.
Okay.
Yes, and please, can you roll this little screen on right hand?
Okay, so now I think I can begin with the lecture, right?
Yeah, thank you.
Yeah. Okay, so let me start. So this lecture will be about complicated motion as we find it in delay differential equations about things which have been proved in the past. And in the beginning, I should like to give a little kind of survey about what has been accomplished. Let me begin with equations where we have a constant delay. See the simple looking equation in the line number 3. The f is just a real function. And this inequality, what you see, means that the equation describes negative feedback with respect to the constant solution, the zero solution, and of course with this delay 1. Here you see again the initial value problem. One prescribes a function on the interval from -1 to 0. This is phi. And then there exist solutions which are continuous and satisfy the differential equation for positive t. This is the x, and the x lives forever in this simple looking kind of equation. And again, let me recall what plays a role here in the description of solutions in a geometric setting. These are the solution segments. This x sub t in C is the piece of the solution on the interval from t-1 to t, but shifted back to this initial interval from -1 to 0. And then also
these solutions, or better these segments, they define us a semi-flow on the Banach space C. You see the relation. Take a non-negative time, an initial function, go to the segment of the corresponding solution at time t. Now, how about chaotic motion in this class of equations? Well, the first results, which could be shown in this direction, establish what may be called a Poincare scenario of chaotic motion. This is like the situation which Poincare first observed in 1899. So that means there is an unstable periodic orbit, which is hyperbolic, which means the dynamics close to the periodic orbit is relatively simple, only exponential behavior for solutions close to the periodic orbit. And then the important ingredient is a homoclinic flow line, which goes to the periodic orbit as t goes to minus infinity and as t goes to plus infinity. And then one also needs some kind of transversality along the homoclinic flow line. And this is some intersection of stable and unstable manifolds. And then, having that, one can conclude that close to the homoclinic flow line, there are solutions which behave in some sense chaotically, which means if I describe the motion along the periodic orbit in terms of a Poincare return map, then one can embed a Bernoulli shift into symbols. This is the prototype of chaotic motion into this Poincare map. What one can also do, and this is a specialty of these delay differential equations, in some cases one can also embed these chaotic interval maps, which are much simpler, into a Poincare return map. And this is these chaotic interval maps, they are not one-to-one. And in these delay differential equations, it also happens that different initial data can produce solutions which merge, which become the same after some finite time. And this makes it possible that one can embed these chaotic interval maps in Poincare return maps for special equations. Now, here are a few references. I mean, very important is this paper by Mackey and Klaas in 1977. This only contains some numerical simulations, but they seem to show some complicated solution behavior. And their work stimulated a lot of other people to try to prove existence of chaotic motion. And then I think the very first paper, this is due to Hubert Peters in 1980, he looked at an equation as you saw it before, but with an f which is discontinuous. This is a very special case, but he obtained chaotic motion. And then later on, for equations where the f on the right-hand side is a nice differentiable functions, there were quite a few results. Now, where does this chaotic motion come from? I mean, this equation which you saw, simple as it is, there can be only one ingredient in the equation which is responsible for the chaotic motion, and this is the shape of this nonlinear real function f. And the rule of thumb is that for this equation which you saw, we have, let's say, simple dynamics, no chaotic motion if the f is monotone. But for certain f which are not monotone, which have local extrema, at least one, then one can get complicated motion. And in particular, the last result by Lani Weider from the year 2001, what he accomplished was that he really, for a class of equations which only have one local extremum, he could, for such equations, he could establish chaotic motion. But one has to be a little bit careful about interpretation of numerical results. There are cases where if you look at the simulations, at the solutions, they seem to behave in an unpredictable manner. But on the other hand, there are also, let's say, recent results about periodic solutions where you also, if you just simulate them, they seem to be chaotic for the naive person who looks at this, but they come from periodic solutions which do have stable orbits in the space C. There's one result, I'm not so sure whether it's still in preparation or whether some progress has been made by Benedict and Christie not so long ago, who constructed such periodic solutions which look complicated if you only simulate them and look at this. Okay, so let's proceed to variable delay. That will be the topic of this lecture, basically. And let's begin with an example. Look at this equation number 1. The parameter alpha is a positive number. R is, so to say, the maximal delay in the equation, and the d of x of t, which you see there, the d is what may be called a delay functional, defined on a set of functions from the initial interval from -r to 0 to r. So this equation, you might think that it's linear, but it's not because of the d. If the d were constant, it would be linear. And in that case, you also would be in this negative feedback situation from the example which I showed you beginning with the constant time lag. And in that case, everything is known. For almost all parameters, the equation is hyperbolic, or if you wish, the zero solution of the linear equation is hyperbolic. Very simple, everything is known, no complicated motion. Let me interrupt this a little bit and just recall this basic result about well-posed initial value problems, which applies to equations with a state-dependent delay. Here you see the space of continuously differentiable functions on the initial interval. You have an f, which is continuously differentiable on an open subset in the space C1R. You see this initial value problem in the third line. And then if this additional condition, which I mentioned yesterday on smoothness of f is satisfied, then we know that the set xf, these so to say initial data, which satisfy this kind of compatibility condition, it's the differential equation at t equals 0, by the way, that this set actually is a continuously differentiable submanifold, well, unless it is empty, of codimension n. And on that manifold, the initial value problem is well posed. We get a continuous semi-flow on the manifold, and the solution operators, which form the semi-flow, the time t maps, they are all continuously differentiable. Let me also briefly recall what this additional smoothness property E was. It's required that the derivatives df of phi, for phi in u, have linear extensions to the bigger space of only continuous functions. This is CR. And then that this map, which you see at the bottom, which assigns to each pair phi in u, where I differentiate, eta in the big space of only continuous functions, this extended derivative at phi applied to eta, that map should be continuous. Okay, so much about this. I mentioned also how this is related to an older condition by colleagues from 1994. Now, how about complicated motion due to state-dependent delay? So see, now we know a little bit about the form of a nonlinearity in the very first equation which you saw with the constant delay, how that may be responsible for chaotic motion. Now we ask, could it be that also the state-dependent alone creates some complicated motion? And of course, in order to investigate that, this equation which you saw with the state-dependent delay, the example, this is suited very well because the only ingredient in the equation which can cause chaotic motion is this delay functional. Yeah, and this is why in the sequel I will be talking about results for this particular equation. Yeah, no f. Only that equation. Well, how about results which have been obtained since, let's say, about 2015? First of all, one can find a delay functional, so that in this equation number 1, there is a solution which is homoclinic with respect to the zero solution. Well, here I should recall that there is another scenario which leads to chaotic motion, not due to Poincare, but to Zhilnikov in the early 1960s. And he discovered that if you have an ODE in R3 and R4, which has a constant solution 0, and you have a solution which is homoclinic with respect to 0, not to a periodic orbit. And then also you need some transversality that also close to that homoclinic solution, you find some complicated other solutions. And in case of our equation with a state-dependent delay, we can prove similar phenomena. For example, that we get solutions on the whole real line close to the homoclinic solution, so that if you go to -infinity, that you see complicated motion, chaotic histories. But also we can do that in forward time. These are these papers which you, in particular the paper by Bernhard Laniweider and myself of 2016. There's also one other result on chaotic motion which is caused by state-dependent delay. This is this paper by Ben Kennedy and Mao and Wendt. They look at not at an equation like number 1, but an equation which also has a nonlinearity like the f in the very first example with the constant delay, and this f helps a little bit. And they do not use this whole setting with the solution manifold and so on. But nevertheless, they also show that there exists some chaotic motion in a particular example, and the motion comes from a combination of the state-dependent delay and a nonlinear function in the equation. Now, all these results which I mentioned up to here for constant delay and also for state-dependent delay on chaotic motion have one thing in common, namely the chaos which one proves, the chaotic motion in all of these examples occurs in a very small subset of the state space, of the C1R, or in for the equations at the beginning with constant delay in the space C, in a very thin set, like a Cantor dust. It's very thin. On the other hand, if you look at numerical simulations, then they suggest, I should carefully say, that complicated motion actually occurs in a larger set. So one is tempting to ask, for example, could there be a flow line, so a curve of segments t to x sub t, which is dense in an open set? Dense means that the closure of the trace of the curve fills the whole open set, which practically means that the x sub t's, that over and over again, they come arbitrarily close to any point in the open set. This is something which sometimes is called turbulence in other work on chaotic motion. Of course, here where we have the state space, the state space is the solution manifold, so we would look for density not in an open set, say, of the space C1, but in an open subset of that manifold. Now let me immediately continue and say that I will not achieve such a result about density of such a curve of segments in an open subset of the state space, but something which is closely related to that, and something which also proves or verifies what you think you see in numerical simulations. Now let me begin with this first result, now 3 years old. I'm always talking about this equation number 1. Take the maximal delay in the equation to be 10. 10 is large. Then the result is that there exists a delay functional d defined on some subset, capital Y, of the space C1R, and also the parameter in the equation is it's actually close to pi over 2, a little bit larger, so that first of all the initial value problem for our equation is well posed for initial data in the set Y. And then the main assertion is there exists a continuous differentiable solution of the equation number 1 with this particular delay functional d, so that the so-called short solution segments, that they are dense in the full Banach space C11. What was C11? C11 was the space of continuously differentiable functions on the interval not from -r to 0, but only from -1 to 0. And the short segments, they are just segments over intervals of length 1. Take the solution between t-1 and t, shift it back to the initial interval now from -1 to 0. This curve is dense it fills, so to say, the whole Banach space C11. Well-posed in this context means only that we have existence and uniqueness of solutions if we take initial data from the set capital Y. Now how about, and dense of course means that the closure of the forward orbit of the short segments fills the whole Banach space C11. Remember, the one at the bottom, the index at the bottom means that the R is equal, or the interval is from -1 to 0. Now how about the set Y? Well, in this result, Y is not what we would like to have, namely a solution manifold. It's a somewhat strange subset which is constructed in the course of the proof of that theorem, and one can say Y it has infinite dimension, but if you would be able to define a codimension for the whole set Y, which is not possible, by the way, it contains pieces where you can talk about a codimension and its infinity. Yeah, so it's somehow strange. And this, of course, is not very satisfactory. So the next problem was, well, could you also find an example of a delay functional so that you get short segments which are dense in an open set, but now of a flow line of a solution with segments in the solution manifold, so where you can apply your theory about the semi-flow and the continuously differentiable solution operators. And this is the content of the next theorem, which I would like to show you, namely, actually there exists an R and an H. H plays the role of the number 1 in the former theorem, and a delay functional on an open subset in C1R. Now you see the U is an open subset, so that this functional F, which you see here, this is exactly what describes the right-hand side of our equation number 1. Yeah, that this thing is continuously differentiable, satisfies the additional smoothness condition E, and now comes the main thing. So that equation number 1, well, there's an alpha, the alpha here is simply 1, has a continuously differentiable solution whose short segments, now short segments over the interval from -h to 0, not from -1 to 0, that they are dense, well, no longer in the whole Banach space C1H, but in a certain open subset of the space C1H. So one has to pay a little bit in order to get this better result as far as smoothness and regularity is considered. One only gets density in such an open subset. And of course, because of the properties of F, which I mentioned, now the initial value problem for that example is well posed on the solution manifolds, and we have these continuously differentiable solution operators. Now in the rest of the time, I would like to talk about parts of the proof, yeah, so that at least you get an impression of what is being done. Now the steps towards the construction of this delay functional, they are as follows. The step 1, which is, well, it's really a crucial step, but first of all, in the step number 1, we want to find the R and the suitable H, and not immediately a delay functional, but something simpler, a function from the non-negative reals to the interval from 0 to R, so that this equation, yeah, where you see the capital delta of t, but not a delay functional applied to some x sub t, so that that equation has a solution which is twice continuously differentiable, whose short segments are dense in an open subset of the space C1 of functions on the small interval from -h to 0. So, of course, one has to find this open subset and so on. This is another task. So this equation, which you see here with the delta, this is linear, but it's non-autonomous because of the delta depends on t. How do we begin? Now, first, well, we find somehow some h, positive number, and a sequence of functions kappa j, which live on the interval from -h to 0, which in the short interval from -h over 2 to 0, they are decreasing and they are positive. And the important property is that these functions on this little interval, that they are spaced at a certain distance. Yeah, they have a difference which is bounded below by a constant. This is very important, and it's also important that this distance is measured in the C1 norm, the norm of the space C1H, and not the C0 norm. Yeah, this is also something which is crucial. And the next thing already is the preparation for this kind of turbulence or chaotic motion. Well, we take some suitable bounded open subset. I don't tell you how this is done, but in an open subset of the space C1H, of course, restricted polynomials are dense. So we take a sequence of restricted polynomials which are dense in a bounded open subset of H, and then we rearrange the sequence of these restricted polynomials like this. Well, this is something which is always being done if you are familiar with verification of chaotic motion and embedding of symbolic dynamics. You begin with the polynomial P1, then P1 and P2. So you repeat the previous step, then P1, P2, and now you add the next one, P3, and so on. Yeah. And later on, we will construct a solution so that in this order, the P1, P1, P2, P1, P2, P3, and so on, that appear in the course of time as short segments of the solution which we are going to construct. And then we concatenate, which means think of this function kappa 1 on the interval from, no, we take the beta 1 on the interval from -h to 0. And then we have beta 1 at 0. And then we shift our kappa 1 from the other sequence to the interval from, let's say, some epsilon to epsilon plus half. So we have two functions, and we connect them in a continuous way or continuously differentiable way. And the result is the function zeta 1 from the interval from -h to plus epsilon plus h. Yeah, here again you see the kappa 1, and here you see the beta 1, and from this sequence of chaotic polynomials, and here you see this concatenated thing, the zeta 1, which is defined on the interval from -h to h plus epsilon. Okay, now to begin the construction of the desired solution and of the delay function only, we take an initial function in C1R, which is like the kappas. So it's decreasing in positive on the interval from -h over 2 to 0. And now comes something important. We choose the delta of t on some interval from 0 to capital S, so that the delayed argument in the equation, in this linear equation, the t minus delta of t, is negative. Yeah, but if t minus delta of t is negative, then x is equal to phi, and phi was positive. So that means the equation tells us x prime of t then on the interval from 0 to s, because of this delay differential equation, is negative. So the x is strictly decreasing, and then we can make it decrease to some negative value at x of capital S. For example, if you take delta of t equal to t on some interval, you make s large enough, then you get that. Now we pick some time capital T, relatively large, s, plus the length of the interval on which this concatenated thing was defined. Yeah? And then we can find a continuation of the delay functional in such a way that the solution of the linear equation on this longer interval from 0 to capital T on the end part of this interval from t minus h minus epsilon minus h to t, equals the translate of C1. Remember, C1 contains a piece which is a polynomial from the sequence of polynomials which is dense in an open subset. So that one can do, and let me try to explain this a little bit by means of the thing which you are going to see here. Here you see again a piece of the initial function phi. Here you see what I told you before. We can find the delta in such a way that the solution which starts at phi of the linear equation with the delta of t is decreasing until time capital S. Here you see on the right hand side a shifted copy of this function C1, this concatenated thing. And the endpoint is the interval capital T. And then by the technique, well, I did not really explain it, but I said one can do that, which resulted in the piece of x until time capital S. We can also choose or continue the function delta to the interval from S to capital T minus 2h minus epsilon, so that the solution does what we want. This is the dotted line which you see there. And then furthermore, we can also choose our capital delta in such a way that the solution of this equation, which contains the delta, coincides with this shifted copy of this concatenated thing theta 1. Yeah, so the whole graph which you see, including the dotted part, this is the solution which we can construct. Yeah, let me try to explain a little bit why this can be achieved. Now, see, if I take little t between capital T minus 2h minus epsilon and capital T, and then I can choose the function delta of t. Little t is between these points which I just mentioned. Yeah, it is increasing. Then I can choose the delta in such a way that x at t minus delta of t, that picks up values which are positive or negative, which I have already. That's the previous part of capital X until time capital T minus 2h minus epsilon. And I can choose the delta in such a way that I pick up, by going to minus x of t minus delta of t, values which are just the derivative of this shifted copy of theta 1. Yeah, and then I'm done. If I have achieved that, yeah, then my solution necessarily coincides with the shifted copy of theta 1 on that interval. Yeah. Doing this is a little bit technical, but it's, in a way, it's elementary. Okay. By arguments like this, we get from our chosen initial function phi the solution on the interval from minus r to capital T. And then the next step is I replace phi with x sub t, with this long segment from t minus r to t, and then I repeat the whole process. Remember, on the previous slide, you could have seen that xt has the same properties as phi had on the interval from capital T minus h over 2 to t. So I can repeat the process. But in the next step, of course, I get a piece of the solution which coincides not with the shifted copy of theta 1, but with theta 2, and so on. Yeah? And theta 2 contains another piece of the sequence of complicated, of these dense polynomials. Yeah? And then I continue and concatenate, put all these pieces together, and this gives me finally my solution x on the whole interval, well, from minus r to plus infinity. And also, in the course of the construction, I find this delay function delta. And then the next step, or better the plan, would be to convert this function delta to a delay functional on the trace, on the segments of the solutions which has been constructed, the x sub t's. Of course, in using this formula, but in order to use this formula, I would need that the curve which sends the little t's to the x sub t's, that this curve is injective. Yeah. So this is something to achieve. And then the next step in the plan would be having the delay functional on the trace, one should be able to extend this D from this curve, this one-dimensional object, to a full neighborhood U of the trace in the space C1R of long segments. And then finally, one would have to achieve the smoothness properties which we wanted, namely this extension property for this delay functional F, which is given by the D if you look at the last equations on the screen. Okay, so the first problem is this curve of segments of the solution which we have constructed one-to-one. Well, this can be done. The next question, which is related to the problem to extend D to an open subset, then it would be good that the trace of the curve on which I can define the D by using the delta, it would be nice if this trace would be a submanifold. And in order that the trace, so the collection of all the x sub t's, is a submanifold, it should certainly be the case that we do not have accumulation of segments xt at some particular xs, then it could not be a submanifold. But that is a bit problematic. Namely, on one hand, we want to achieve that the short segments, the x at certain times tj, where they are the same as these beta j's, that these fill an open set. So they are return also to each other from time to time as tj goes to infinity. On the other hand, we want to have that the long segments, the x sub t's over intervals of length from -r to 0, that they do not accumulate at each other. So this seems to be contradictory, and it's in no way obvious that we can achieve both goals in one construction. Okay, so this was the step number 1, and with certain things which we would have still to achieve. Step number 2 is injectivity and what I call separation. Now, remember, we began the whole constructions with these functions kappa j, which had a certain distance from each other. And the long segments, the x sub t's, this was our construction. They contained the shifted copies of the theta j, and the theta j's contained the kappa j's. So using that, one can achieve that the long segments along our solution, that they keep a certain minimal distance from each other. Again, it's important in the C1 norm. If I take long segments x sub t and xs from disjoint arcs along the trace. So t is between j times capital T and j plus 1 capital T, s is between k times capital T and k plus 1 times capital T, but the j minus k, they are not neighboring, so I have the distance larger than 1. So the arcs, which are, in other words, arcs along our curve, which are not neighboring, they have a minimal distance from each other, and this is important. It's not possible to get a similar result with a norm on the bigger space CR, by the way. Okay, so let's briefly go to the next thing. This is related to how to achieve this smoothness property E. This is a different topic. Look at this proposition. Suppose we have a map G, which is continuous differentiable on an open subset of C1R, and locally for every point phi, this G is the restriction of a map capital G on a little open subset of the bigger space of only continuous functions. And then one can conclude that this G has property E. So this proposition will be applied to the delay functional D, not to the F. If I rewrite our example in the general form with a nonlinear functional F, then this F will not have the property that it is the restriction of, let's say, a capital F, which is continuously differentiable on the big space C. Something like this is never satisfied if you look at examples with state-dependent delay. But with the D, with the delay functional, which is only an ingredient in the nonlinear functional F, that is possible, that the D comes from something nice on the bigger space. So this proposition will be applied to the delay functional D, which we do not yet have. Okay, Now, step number 3 about injectivity, and then we can convert, as I told you before, the delay function into a delay functional, but only along this one-dimensional curve, yeah, by this formula. So here you see it again. D of xt is defined to be delta of t, and this is possible because the curve is injective. But then the next question is the trace, so the collection of the segments, how good is that as a subset of the space C1R, and this will be important also of the subs of the big space CR. Well, what one can see is in the course of the proofs of injectivity, one gets what you see here, this curve T to xt as a curve in the space CR. It's continuously differentiable, it's injective, and the tangent vectors, these x sub t prime, actually are also the tangent vectors to this curve. They are never zero, and from that one obtains, of course, that arcs, pieces of the trace between, for parameters t, between some non-negative numbers a and b, that they are in fact continuously differential submanifolds of the big space CR as we would like to have it, but we don't get that. And of course also that then this map, the curve, is a diffeomorphism from the interval to the curve. This is nice in the space CR. And from that we get, of course, that the D given by the formula in the third line above is continuously differentiable on these arcs, on these pieces of the trace. But what we do not get is that the whole trace is a submanifold of the space CR. Yeah, that we do not get. So it's a bit technically. So the next step is what may be called semi-locally into the big space CR. What means into the big space? We want to continue the D, which we only have on this trace, and we know on parts of on arcs of the trace it's nice, it's smooth. So what one has to do, and this is very technical, one constructs neighborhoods, U sub j, neighborhoods in the space CR of these arcs x capital J. So the little t runs between j times capital T and j plus 1 capital T, and continuous differentiable continuations of the D, which we in the beginning only have on the one-dimensional curve, to this open set Uj in such a way, and this is quite technical to achieve this, that if I consider neighborhoods Uj of neighboring arcs, xj and xj plus 1, that on the intersection of such neighboring arcs, these constructed extensions or continuations, that they are the same. But that does not exclude the possibility that on an intersection of Uj with some Uk, and k is not j plus 1 or j minus 1, that then these constructed continuations, that they differ from each other. In general, that will happen. Yeah, so we are not that far. But this is achieved in the next step, number 5, how to get the desired delay functional globally onto an open subset of the space C1R. And it is here where these separation results come into play. You see, I can reformulate them that the distance with respect to the C1 norm of arcs xj and xk, which are not neighboring, yeah, that they have, the distance has a positive lower bound capital A. Yeah. So now I can do the following. I form neighborhoods n sub j in the space C1R of radius capital A over 2 of the arc x sub j along my solution. Yeah. Then by the separation result, I know that nj and nk have empty intersection if they are not neighboring, if j minus k is larger than 1 in modulus. Okay, but then I may define d of phi, our desired delay functional, by dj of phi on the intersection of uj with nj. This is still an open neighborhood of the arc xj, but only in the space C1R, yeah, because the nj is only in the space C1R. But now everything makes sense. Yeah. Now, because and this is automatically a continuously differentiable continuation D to the set U, which you see on the line next to the bottom. This is the union of all these UJs intersection with NJs, and they form an open neighborhood of the trace. And this is basically what we want. In the final step, one verifies the property E for the nonlinear functional f, which represents our differential equation. The proposition, as I told you, gives us, remember that D locally is the restriction of something on an open set in the space of only continuous functions, not globally, but locally. And this is where I can apply the proposition. And that means D has property E. And then that here it's repeated that the equation number 2 is just this general equation number 1 if I take this f. And then I can compute the derivative of f. And now knowing the extension property E for the delay functional D and having the formula for the derivatives df of phi, one can verify that also f has this extension property E. So this is finally how one gets done and achieves everything what one wants. Okay, so thank you very much. I have one last thing which I can show you, a few comments. One problem is left open. You could not see this from what I told you, namely the D which we constructed, which came from this delay function delta, is such that if I follow the delayed argument t minus d of xt along the constructed solution x, that this is not always increasing. It goes forward and backward. Yeah, after some times it moves forward again. Okay. And that was an open problem. And let me just tell you that in this paper by Kennedy, Mao, and Wendt, they obtained a delay functional where actually this delayed argument along the complicated solutions is increasing. And the paper by them is not in the setting with the solution manifold. Well, meanwhile, I also have a result in the solution manifold where one gets complicated motion for a D where the delayed argument along the solutions is increasing, but one also has to pay a little bit about that. One do not get any longer density of short segments in an open subset of state space, but only in another set which is also large in a certain sense, infinite dimensional and so on. And then finally, almost finally, we always talked about density of the short segments, but what we are really interested in is the flow line, the curve of long segments. So what are the implications of the turbulent curve of short segments for the flow line in the space in XF C1R? Well, let me just say here that one can formulate this going to some quotient spaces and so on, and then you also get density of that flow line in an open subset of a certain infinite dimensional Banach space, I should say. Yeah? I have no time to go into details. So here, let me thank you for your attention very much. And okay, there's the big question. Could we get a delay functional with a turbulent flow line of long segments? This is wide open at present. So sorry for taking your time. Thank you for your attention in the end.
Thank you, Professor Walther, for your interesting lecture. There are some questions. The first one, is it correct for such solutions, complicated motion, to pose the question of Lyapunov stability?
I did not get the last word, so it was related to Lyapunov stability, right?
Mm-hmm. Yes.
Well, of course, these solutions they are unstable. Is that what really answers the question? I'm not so sure.
Okay, there are also several questions in one. Calculate Lyapunov exponents. Is it correct for such solutions?
Okay, no, sorry, then maybe I misunderstood about Lyapunov exponents. I don't know. I never tried to do something in order to find out something about Lyapunov exponents. I mean, that's another way to formulate results about chaotic motion using Lyapunov exponents, but I did not look into that. So that's also something which one might try to study. It's wide open. Maybe interesting.
Okay, thank you. And also, next question. Can differential equations with delay have applications in the theory of semi-Markov processes with the delay in screen?
Say in which what I didn't get the last word. Sorry. In which theory?
In the theory of semi-Markov processes with delay in screen.
Well, the point is the example which I constructed in these results, they are, I have to admit, completely artificial. Yeah. So I think I cannot say anything about applications at this point. It's only that the phenomenon that state-dependent delay alone, this is the message, that can produce chaotic motion, and chaotic motion which is not restricted or confined to a very small set in state space. That's all.
Okay, thank you again for lecture and for answer questions. And now we have a break for lunch till 3 p.m. And I also want to remind that you need to use a new link for next 4 lectures. Thank you.
So thank you very much from my side.
Have a nice day.
Thanks.